evening, Fancy Meat Computers. How is everybody doing today? Welcome to Chill Stream, the chillest stream of all the streams. Chill Stream, oh yeah. So, let's see here. Could I quickly talk about 64-bit operating systems? What parts of the systems have 64 bits of memory, and what parts remain 32-bit? Well, it's kind of outside of the... That's a question that sort of lies well outside of the material that we've been studying. And I've been studying in order to be able to talk to you guys about it. But I can take a shot at it. So, when you have a 64-bit system, that means that 64 bits is the word size of the system in its totality. So, pretty much everything would be 64 bits, right? The size of the registers inside of the CPU would be 64 bits. The size of the, the width of the memory cells in memory would also be 64 bits because, of course, you load one memory cell into one register, so they should be the same size. The instructions themselves are likely to be, though the instructions themselves may be less than 64 bits in size, they may occupy 64 bits. I'm not actually sure when you get into those types of architectural details whether that's true or not, but it would strike me a lot of these types of, optimizations are going on in ARM. And I'm not going to say that they aren't also going on in Intel, but or the sort of the larger chipsets. It's just you have more bits to play with 64 bits, so you don't necessarily people will be finding these sorts of efficiencies and exploiting them, but you just have to, I'm sorry I'm not answering this very well. It's kind of like you would have to study an Intel processor in the same depth that we're studying the ARM processors in order to be able to answer that question. But it should be pointed out that the ARM processors that we're working with are 32-bit systems. And that turns out to be good enough for most applications. So, let's see. Let me see if I have any announcements. I might have announcements. Oh, so I posted a little bit, a couple of sort of bonus things under extra resources this week. One was an external resource that was forwarded to me by a student, and I thought it was, sufficiently interesting to post, and I think probably some of you guys will be able to make use of this information. This kind of goes, how I criticize the slides for diving right into the small details but missing the big ones? This one goes over some of those larger details, so that might be useful to you guys. But yeah, so that's like an extra study aid. And the other thing that I posted was a video on the YouTubes, which I'm not going to play because I might get a copy strike. But it's a video from a channel that's been kind of a a favorite of mine over the last couple of months, Sebastian Log. He's a video game developer that actually shows you like the math that goes into like ray tracing and that sort of thing. So he did one on the logical circuit that results in the ability of a computer to store memory, which I thought, although we're not necessarily concentrating on that in this class, probably, it's a really good illustration and demonstration, so if it's of interest to you, I would definitely recommend it. This may be a funny question, but is it possible to have a powerful chip like the Intel Core i9 on a small microcontroller like the size of an Arduino? To quote The Hunt for Red October, possible, but not recommended. So the problem with the Intel chips, and the reason that they're not used in embedded systems applications, generally speaking, number one, they're not really designed to communicate in the same way that ARM chips communicate with peripherals. Like, ARM chips communicate via GPIO very easily, and they're configured and made for that purpose, right? Something like your Intel chip, Intel chips are generally configured to communicate via data buses. The types of connections that an Intel chip make, you'd never dream of soldering yourself or putting something together yourself, right? It's just too complicated. So that's kind of like their target application. So, but the question is, would you be able to take an Intel chip and do something it's not intended for, put an Intel chip in a kitchen timer? And the answer is, you absolutely probably could make it work. The question is, how long is the battery going to last? The thing about Intel chips, very powerful, but holy hell, they are not battery friendly. They are hungry chips. And the other problem that you start running into is power or heat dissipation, right? Like when you have an Intel chip running, those things heat up. I probably don't need to tell you this, but they heat up. And, I don't know how much it is, but probably a fifth to a quarter of the space inside of your laptop is dedicated to ventilation, just to keep the CPU from melting. You don't have that problem with ARM. Not as much, because it's been optimized more for low power consumption, particularly the smaller model numbers. That's how it kind of works, is the smaller the model number, the more energy efficient, and the smaller the chip. But yeah, hopefully that answers your question. I see the winner today is Top Hat. People are feeling Top Hat today. 26% of people are feeling Upside Down. 37% are feeling Top Hat. 18% are feeling Plain. And plain as in... oh, that's a pun I didn't realize. And then 18% are also feeling like old grandmas. Thermal paste. Yeah, I mean, again, you can, heat dissipation is a whole nother problem. And, not the subject of my class. Heat dissipation is something that you'll talk about when you take thermo next year. So yeah, or possibly this year. I don't know. You're going to take a thermo course at some point, and you should save questions related to heat dissipation for that. But yeah, NVIDIA omelet for sure. Have you seen the new GPUs that are more fan than chip these days? I remember when a GPU didn't even have a fan on it, a dedicated fan on a GPU. What's that about? Yeah, anyway. What about AMDs? AMD is basically in the same boat as Intel. Both the AMD processors and the Intel processors are what you call complex instruction set computers. So they're both like, will give you a huge number of instructions, and we're big chips. But yeah. Oh. Yeah, 3 fans, yeah. All right. Anyway, so last time we were talking, we finished off general purpose I/O, and now we're on to general purpose timers. So we're going to talk about timers today. So I have a couple of things that I want to say about time. Oh my goodness. Zoom. Stop. This is too much zoom. How did I even do that? There we go. So there are a couple of things that I'd like to talk about timers that's sort of not on the slides, that sort of set the stage before we even get there. So first, we should be very specific about the type of timer that we're talking about, right? What we're talking about are peripheral timers. So these are timers which are dedicated chips, dedicated ASICs that are external to your processor that are communicated with via the GPIO interactions that we have been studying previously. You know, if you want to wire up a separate one, if you've got one included on the board, which your boards will have one included, then there's memory map. There's some memory which has been mapped to these timers, which you're free to use in the same way that you use them for GPIO. Question: so ARM chips can work? So can ARM chips work on laptops? Yeah, some laptops do use ARM chips. I'm pretty sure. Like, I don't know. It depends on what you consider a laptop. So you know those Windows tablets they had a few years ago with the keyboards that fold up? There you go. ARM chip. If you consider that to be a laptop, then that's a laptop running on an ARM architecture. And you know, I gotta look it up now because I'm curious. I'm curious whether the Chromebooks are running on an ARM processor. I'm pretty sure they would be. Chromebook processor? Oh no. Oh, there you go. No, they're on Intel. Wait, yeah. Oh, there you go. I stand corrected. Laptop ARM processor. Yeah, okay. So, like, there's some dealios like this. Generally, the more tablet-y looking ones, sometimes. One of the things you got to be careful with, I wouldn't want an ARM processor on a laptop because they lock you out of the bootloader. But, and you know me in Linux, I got to have access to my bootloader. Raspberry Pi is ARM, yep. New MacBooks? Maybe. Chromebooks are on Celerons and Atoms, yep. M1 Macs are ARM-based. Well, there you go. So Macs started using them. But yeah. So, back to timers, though. So the timers that we're about to talk to are kind of... They use as raw input an oscillator signal, like a clock signal, right? Like a very important input to a timer is either the internal or an external clock signal, right? Without a clock signal, what are you like? You can't even time anything. So I'd like to put a question to you guys. actually. Why do you think that what do you think the benefit would be to having an external timer? Why wouldn't we just put commands in? Like, why wouldn't we just time in software? Because you can do that, right? Like, you can totally write a program in C that times things. Why would we want to do this in hardware versus software? I'd like to see what the class has to say about that. Efficiency and memory conservation. Possibly. Software is variable based off processor speed and age. Physical oscillators are more accurate. Yeah. Is an external timer more accurate? Meaning if the software slowed down, wouldn't the timer as well? Yeah. In case errors occurred in the software. Yep. Good reason. Good reason. Yep. If we put it into the software, wouldn't there be small delays because one command runs after the other? Yep. It can't be done. It can be done in parallel. I think the processor would need to keep track of the counter manually. Yep. Software lag. Yep. If something goes wrong, it is easier to fix the problem. Find the problem or fix it. Yeah. So, in general, I'd say you guys have the idea for sure. So there are problems with expecting software to be able to time things accurately. Number one. Unless you're programming in assembly, you don't have a good idea of what instructions are being executed when, because the compilation process is opaque to you, right? So because you don't know what commands are getting executed when, how can you time anything accurately? Like, you might be able to time things within, like in the milliseconds range, right? But if you need something timed in the same type of on the same scale as the oscillator in the chip itself, definitely you're not going to be able to achieve that with software at all. Like if you need to time stuff in the microseconds or even the nanoseconds range, depending on how fast your oscillator is. A hardware timer is basically the only way to accomplish it. The other thing about timing things with your software is, so you've got this timing code that's set up and it's running. What if it gets interrupted? Does not your timer also get interrupted? The answer is yes. So because it's external, it's independent of anything that's going on in the software. And as we're going to see, external timers can be configured so that they cause interrupt in your software. So this is essentially, when we're talking about timers, we've got two main modes that we're interested in the applications of. The first mode is comparison, and the second is capture, right? So with capture, you're trying to time things. It's an electronic stopwatch, right? With comparison, you're waiting for the time to hit a particular fixed point or a fixed, duration, and then you generate a signal. You generate I'm sorry, that's backwards. You generate a rising edge, right? And that rising edge can be taken and interpreted as an interrupt signal, which can produce software effects and all kinds of stuff like that. However, Grish, I would say that wiring up making the timer a hardware peripheral actually makes it less easy to find it if something's gone wrong with it, but it's also going to make it a hell of a lot more reliable because, generally speaking, when you buy a chip you can trust it, especially if it's something as basic as a timer. So how do timers work? Excellent question, me. Oh, wait. Yeah. So, in addition, like, there's one other thing that we're going to talk about, which is pulse width modulation. I will tell you what pulse width modulation is once we get there, but that's another thing you can use timers for. It's got the coof. It's quite similar to the idea of generating an interrupt, but we'll get there. Well, in effect, it's very different from generating an interrupt, but the electronic process by which the interrupt signal is generated is the same as the process by which a pulse. It's similar to how a pulse wave is generated. So let's examine a timer. So I'm going to start on this half, and then I'm going to go back to that half, okay? So let's just imagine we have some clock signal coming into the counter, right? So counters, as you might imagine, count. So timers count. They are counting circuits. That's like in a very real way, that's all they do, right? Timers can be configured in one of 3 different modes, which are perplexingly much later in the slides than they should be. So timers have 3 modes. You can count up, you can count down, and you can do center counting, right? So with count up, you start at 0. Each pulse that you receive from the clock increments the counter by 1 until it reaches some specified auto-reload value. Once it reaches the auto-reload value, the counter resets to 0, and then counts up to the auto-reload value again. So, you also have countdown mode, which counts from the auto-reload value down to 0, and then resets itself back up again. And then you have center counting, which counts up, hits the auto-reload value, then counts down, then up again, etc., etc., just bouncing around inside that range. All right? So those are your 3 modes. For the time being, let's just imagine that everything is in count-up mode, just so that it's a little bit easier. So we've got the auto-reload register, which contains the auto-reload value with which the counter is reloaded. But essentially, what happens is this thing just counts and counts and counts and counts and counts until it's reset. It does this, and it also generates a certain number of external signals based on its position and value. So the timer we used in Lab 1 was the first one. Shoot. I have a confession to make, class. Despite having signed out a lab kit, I haven't actually done Lab 1 yet. So, because I'm not getting marked for it. Yeah. Thank you, Omar. I should do the labs. If I do the class, if I'm teaching the class, I should do the labs. Sorry, guys. It's been busy. Anyway, yeah. So the timer is counting, right? Let's talk about the prescaler. So the oscillation signal that's coming directly from the oscillator, or the clock signal, will be occurring with some frequency f CLPSC. So you hit a prescaler with that. Yeah. Didn't we use timer 3 and change it to timer 2? What? So, the clock signal hits a prescaler. If this prescaler is set to 0, then it just passes the clock signal through with no alterations. But essentially, the prescaler, it's like another counter, but it slows down the oscillation. So, if, for example, you have a clock signal that is occurring with a frequency of 1 megahertz, but you're only interested in timing things by the millisecond, so you're only interested in timing by the kilohertz, then you set the prescaler value to 1,000, so you get 1 pulse per every 1,000 clock cycles. This allows you to control the frequency at which the timer occurs. It allows you to control the frequency with which the timer counts. But, of course, the frequency can't go any faster than the original clock signal. The prescaler will only slow it down, draw it out. This is too confusing. Let's reset. Essentially that's the overall view of how a timer works. Now we can, oh my goodness, I did it again. So in addition to the auto reload register, which is configurable, there's also the compare and capture register. So the compare and capture register holds the value relevant to both comparison and capturing. You know, as the name says. When you're in comparison mode, you load CCR with the timer value that you want to generate the signal on. So essentially, every time the counter increments, it compares itself to the value in CCR, and if the two are equal, it outputs a rising edge, which can be picked up elsewhere and interpreted as an interrupt. By comparison, if we have input capture, the timer is going to wait for another signal to come to it, and when it receives a rising edge from another location, it will store the current value of the timer in the compare and capture register. So it will capture the current time in that register, and that register can then be read by the software. Isn't frequency of clock count the clock speed advertised on processors? That's a good question. So, generally speaking, I want to say something like, I find it likely that any circuit that you may care to choose is likely to be running on a pre-scaled clock. Like, if you think back to, like, it used to be a thing back in the 90s, at least. You don't really hear about people doing it these days, but it used to be back in the 90s, one of the things you could do with your processor is you could overclock it, right? Which is to say you could increase the, decrease the frequency of the, decrease the period, increase the frequency. You could increase the frequency of the clock signal and get the processor to operate more quickly, normally at the cost of excess heat production. But if you souped up your heat removal, added more fans to your computer, you could overclock your existing hardware and then have it run faster. That would imply that the CPU itself, since that was configurable, what you were actually configuring was the prescaler to the clock signal sent to the CPU, which means that there would be some pre-scaled clock signal which would be running much faster. So I would say the clock speed advertised on processors would be post pre-scaling. So yeah, oh my god. So yes. I would say the answer to your question is yes. Where are the CCR and ARR? Are these stored in memory? Yeah, those would be memory mapped, right? So in the same way that your output data register is memory mapped, so are ARR and CRR. So is timer counter still part of the hardware, or is that now part of the software? No, this is still hardware. So essentially, the timer counter peripheral itself contains a register, which is being incremented every time it receives a clock signal. Actually, if you broke this guy apart and looked at its electronics, it would be probably surprisingly similar, or surprisingly simple. You could probably whip up a circuit diagram for one of these things. Timer chip circuit diagram. Maybe we can find one. Now this is oh. This might be it right here. Yeah, so not very complicated at all. All it really is like a flip-flop in the middle that you add 1 to every time the clock it receives this rising edge. So how would we read the captured time by the CCR using code? Well, we're not quite there yet, but you would be reading it in the same way that you would read your GPIO pins. The same mechanism. Since it's memory mapped, you find the address which it has been mapped to, and you dereference the pointer to grab out the data. Do all timers have a prescaler? I'm going to assume so, yep. Well, like, the crystal oscillator itself obviously doesn't, but yeah. Wait, you're talking about timers. Yeah, all timers have a prescaler. Isn't the prescaler software? If that fails, wouldn't the timer get messed up? No, the prescaler is also hardware. The prescaler is also a hardware component, but it is configurable by the software. So all that the prescaler is doing, right? It's another counter every time, like, so it's very similar to this timer, right? It's also incrementing up to some specified value, except instead of having all of this stuff going on, all it does is it flips, it outputs the rising and the falling edges according to its count, which is then read by the timer counter, or read by the timer as its clock signal. So it's like a timer to a timer, in a way. Yeah. So is the point of prescalers just to slow down the frequency of the clock? Yes. In hardware, is it common practice to use values that are powers of 2 to trigger the interrupt? Just trying to figure out in my head what the physical circuitry is. It's... So, the maximum amount that you would be able to prescale to would be a power of 2, right? Because the register that is contained in here that control that like the prescaler value has the same relationship to the prescaler that the auto reload register has to the timer, right? And like this guy is of a fixed size in bits, so the maximum reload value you can have is whatever that bit width is to the power of 2 to the power of that bit width, right? So the same will apply to the prescaler. However, I would say that probably, like, for most applications, most of the time you're going to be trying to time things in metric units. You know, like milliseconds or microseconds or nanoseconds or something like that, right? So, or like tens of milliseconds, tens of nanoseconds, whatever. So, the actual value that is held by the prescaler is likely to be some kind of, like, some value that brings, you know, this frequency of the clock signal, which is determined physically, so it's not going to line up with metric units, to try to bring it in and bring it in line with metric units. But yeah. Can the timer counter only handle certain frequencies? What is stopping us from just not having a prescaler and sending the clock signal frequency directly to the timer counter? That's an excellent question, David. Thank you. So why have a prescaler at all? The answer is the limited size of the internal register of the timer, right? It's kind of like one of these things where, like, with floating point numbers, where it's like you don't really need, you know, like, in the same way that you don't need stuff to, like, the 20th decimal point, for practical purposes, timing things on a nanosecond scale, there are only really specific applications where that's going to be useful. And it's not like a general purpose application. So, and the other thing to keep in mind is the timer counter, this thing has a register inside of it of a fixed size. Since this is 32-bit architecture, it would be safe to assume that this guy contains a 32-bit register inside of it. So, pulling up, you know, our quick little math. Actually, I have my calculator right here, but it's not an extended calculator. So, if you, 2 to the power of 32, right? So this is the largest integer that you can hold in that, assuming unsigned arithmetic, which is a safe bet in this case. So if you're doing that, and let's say you're like, what's a typical oscillator speed? Quartz crystal oscillator frequency. So, or period, actually. Well, I can figure that out from this. All right. What's the frequency? Range. Come on. Okay, so let's just assume for the sake of interest that let's assume 10 megahertz. All right? So, 10 megahertz, just to make the math go nicely. So 10 megahertz is 10 million, 10 million oscillations per second, right? So 1 over that is the period. So it's e to the 1 times 10 to the negative 7th power. Multiply that by the number of counts that you can hold, right? Copy that. Paste. Paste. Why can you not paste? I'll just do it up here then. So basically, under ordinary power, without a prescaler, your timer would only be able to time 430 approximately seconds, right? And of course, that means that your timer flips. Your timer resets after 7 minutes. Now, 7 minutes might be a very long time for your application, but it may not be a very long time. It depends on your application, right? Like if you want to accurately time something that may take weeks, this is certainly not going to cut the mustard. Now, there are ways of getting around this. It turns out that whenever the timer goes from its maximum value back down to 0, it also generates an interrupt. That interrupt can be picked up by the software and used to increment an internal variable that keeps track of the number of times that the thing has overflowed, right? And you can use that to calculate exactly, how much time has elapsed, like with a very, very fine precision. But the horrible, sad truth of it is that you often just don't need that much precision, right? So the prescaler is a way. It allows you to control the amount of precision that you have, which is, useful because it becomes difficult to deal with too much precision at a certain point. There is such a thing as too much of a good thing. But thank you. That was a very good question. So, yeah. Usually 16 bits in the timer register. Well, under 16 bits you have that's even more problematic. That would be 2 to the power of 16. Which is, if you didn't prescale that one, basically your timer would reset once every 109 microseconds. So what you're saying is it's possible without the prescaler, but just unnecessary. Yeah, it's like, and anything is possible, but like the prescaler, its purpose is to just keep things as imprecise as benefits the physics of the system, I guess. Oh, so timer 2 is 32 bits and timer 3 is 16 bits. So there you go. Why couldn't you just use a crystal that oscillates at a different frequency, or is it just more difficult to produce? Well, how many crystals do you want on your board, Like, maybe that question will be answered here, right? So, well, I mean, maybe not. So, generally speaking, in electronics, if you remember, like, if you look at your actual board and remember what like the crystal oscillator actually looks like, it's fairly large, and it's sort of in a metal casing to isolate it from electric noise. It's Faraday shielded. The oscillator is quite large relative to most electronic components. It's not like super miniaturizable, right? So it really makes sense to have one and then scale that signal depending on what you need from it, right? The other thing is most of the time you won't be adding your own oscillator to your the setup. The board that you're working with, be it an Arduino or a Raspberry Pi or whatever system you're working with, is going to have an oscillator. So sure, you totally could buy an oscillator with the frequency you want and then plug that in and everything will work. But Prescalers are cheaper and smaller. The Prescaler is just for different timers on the same board. Well, it can be used for that. So we can adjust the Prescaler for higher or lower frequency. So technically, if we wanted, we could basically send through the entire frequency of the clock and it just give us a choice to scale it. Yes. Yeah, so obviously the Prescaler can't increase the frequency of the clock, but it can slow it down, right? So the clock is the maximum frequency available, and the Prescaler, draws it out to whatever it fits your application. Yeah. Yeah. Well, yeah, consider lots... when you're considering these things, consider a fairly complicated system, right? But anyway. If you're just talking about a kitchen timer is probably just a 555 timer and a bunch of other stuff and a crystal oscillator, and it's very, very simple. But for the kitchen timer, this is one of your essential components. A Prescaler is like a digital resistor. Well, that's one way to think about it. So, so it is possible to have multiple channel outputs coming from the same clock signal. I won't dwell on this too long, but if you have one clock, it is some of them are configured to have multiple capture-compare registers, which means based on one clock signal, you can have any of these guys doing different functions or, having different values at different times, right? So, again, it doesn't cost anything really to multiply a signal. All you have to do is, pick a line off the wire and run it somewhere else. So, if you had one clock signal and you wanted to have interrupts at 5, 10, 25, and 50, then you could totally do that. Wouldn't incrementing the counter require arithmetic from the ALU? And if this is happening in every clock cycle, wouldn't it take a lot of processing power away from the actual programs? Excellent question, Connor. Thank you very much for asking that question. No, because this isn't being done by the CPU. This is a external peripheral. So the register that's being held here is internal to this. Think of the timer as being a separate chip, right? Think of it this is what we're talking about right here, right? One of these guys. This thing has a register inside of it, and it also has the circuitry to increment that register inside of it. It does not need to pass any data into the ALU in order to increment that register, because the register is not it's not in the memory, it's not in the CPU, it's in the peripheral itself. It's a little tiny piece of memory that the peripheral itself holds. And, it's basically just, 16 flip-flops all done all up, So yeah, no, the timer does not interfere with the operation of the CPU. That's the entire point. But thank you. That's a very good... I'm glad you asked that, because that might relieve some... Oh my god. That might relieve some confusion. So. And this symbol is used for, math in general. It's not necessarily always the ALU of the CPU. So. In output compare mode, we have the timer counter, and we have some constant value. If the two are equal, we generate an interrupt signal. I've kind of already said this. You can configure this in various ways. You can configure it high if the count is equal to if counter is equal to CCR, low if counter is equal to CCR, so you can set it like active high, active low. You can also toggle if the count is equal to CCR, which gets us into pulse width modulation territory. But yeah. How is the capture mode useful? All right. Let's say you have two events for which you have rising edges, right? You want to time the space of time between those two events. You use the first rising edge to capture the start time of the event. You use the second signal to capture the stop time of the event. You subtract the two, and you get the duration over which that event occurred. So that's how it's useful. You can time stuff. I mean, you know, it's kind of funny because it's like, what do you do with a timer? You time things. But yeah, that's so that's what capture mode is useful for. But it's necessary to save the value of the counter register in those instances because you know, otherwise how are you going to save it for later and do the subtraction, right? Yeah. Fancier ones probably perform the subtraction themselves. And oh my goodness. So I was just about to start talking about pulse width modulation, but class is over, everybody. So I guess we'll leave pulse width modulation for next time. What does count equals CCR mean? Does this cause an interrupt? Yes. So, oh my god. So the double equals should be interpreted in the same manner that you're used to. It's a test of equality. So it should be double equals here, to be honest with you. So we have some constant value in CCR which has been loaded by the programmer, right? It's been configured by the programmer. And you have the counter, which is constantly ticking up. Once that counter reaches the specified value, it's like, bah! Okay, interrupt. And yeah, then it sends a signal, which can be interpreted as an interrupt. It's up to you. But you can do with it whatever you want with that signal, but a useful thing to do with it is to trigger a software interrupt. You were thinking about it saving high or low and not the actual count. Yeah, there we go. Would encoders use the capture mode? Yeah, like that's a similar way that that's a similar thing to how an encoder would like the same conceptual framework we're using here to determine the duration of an event could be used to determine the distance between two between two events on an encoder, right? It's like if an encoder is going, right, because like say your car is moving and its movement is being recorded by an encoder, your car hits a speed bump, you know, and that sends an electronic signal, and you record the encoder position. Then car hits another speed bump, you record the encoder position. From those two, you can subtract them to determine how far apart the speed bumps were, right? Is the reload value configurable, or does it come preset on the timer chip? The reload value is configurable. For sure, the reload value is configurable. Although we didn't get through a lot of slides, I feel like I learned a lot. Yay, learning! Yes. Yeah, I feel like we learned a lot this lecture. This was good. We got through a lot of material, even though we didn't get through a lot of slides. So that's good. That's good. These slides are like really dense, you know, and you know, Hopefully I don't have to gloss over too much on the back end, but yeah. Yeah, I think we did well today. I've been wasting a lot of time today playing around with Windows Terminal 2, but to be honest, it's not wasted time because I learned a lot. Yeah. Yeah, anybody who uses Linux will tell you, like, the time you spend just kind of trying to make stuff work is not wasted time because you're learning so much. The counter and constant aren't compared in the ALU, right? Correct. Those are being compared by circuitry contained in the timer peripheral apparatus. Nothing, like none of the operations that are going on here require the CPU, which is why this is why it can time accurately, more accurately than the CPU, because the CPU doesn't touch any of this. The only thing that the CPU does is it may be required occasionally to set the value in ARR, or read or write the value in CRR and receive interrupt signals. That's the only, and those are all just like load store operations. But yeah. Tried using OpenGL, but it hasn't worked. Oof. Yep. Pretty sure you can take an elective on that stuff. But anyway. All right. Are there any further questions? It's kind of funny because I think in this slide deck we don't get to like actually timing things with timers until relatively late. Yeah, here's input capture. We don't get to input capture until slide 27, which is like after we talk about PWM, which I guess like makes it, there is a certain internal logic, but like personally I would have started with the way that timers time. So yeah. All right. Thank you very much, folks. One more of these, and then we're in person, which will be fun. Everybody, your lecture theater for the live lectures is Hamilton Hall 109. Hamilton Hall 109. If I remember correctly, that's one of the nice ones. It's like, man, I have my other lecture this semester is in JHE 376, and like there is a fan in that room that like desperately needs maintenance, and like it's like the audio quality coming over the video stream is like very poor, and but it's not because the camcorder is bad, or you know, the audio capture from the camcorder is somehow deficient. It's because like the level of background noise in that room is like just monstrous. It's amazing how bad it is. So and there's really like, it doesn't matter how good the microphone you buy is. If that's what the ambient sound in the room looks like, no microphone in the world is gonna not pick that up, you know? In fact, having a better microphone might actually make it worse. But anyway, take her easy, folks. Catch you on the flip side.